right, next section. Well, hello, everyone. Next section, I was so excited. I said, no time to say hello. Let's do some concavity. Okay, so now we're going to see how we can use the second derivative to get some visual information about a function. And that visual information is called concavity. So first, let's define what concavity is, and let's try to see what concavity is, and then let's see how we can compute it. So I'm starting with an example where I have two functions here, f and g. So I have two functions. The first one is called f, the second one is called g. And the first thing I'm asking you is to tell me what's similar between these two functions. Well, both functions have the same domain. They're both defined from 1 to 6 inclusively. They have the same range between 2 and 6. They have the same sign. They're strictly positive. They have the same global minimum at 1. At the beginning, we have a local min, which is also a global min. They have the same global maximum at x equals 6. And both functions are increasing over the interval from 1 to 6. So if you're using everything that you know so far, domain, range, sign, local min, local max, global min, global max, and increasing, decreasing, these two functions are identical with respect to those descriptors for those two functions. But they're not the same function, obviously. You look at them, they don't have the same shape. So if we have to enumerate differences, well, for example, they don't have the same inputs everywhere. Like if you compute f at 2 for f, you're going to get 2 point something, but f at 2 for g, you get 3 point something. So they're not equal. So some inputs produces different outputs. But when you're talking about functions, you don't want just to differentiate between y values, because sometimes, you might, use a function that study the relationship between the two quantities, and they will be different just because the way you've collected data will contain some errors. So normally what you want to do is use like descriptors that are more general. So when I look at these two functions, yes, they're both increasing, but they're not curved the same way. So there's a specific notion that will study the curvature. Like if you look at the first function, it looks like f was initially a straight line, could have been initially a straight line, but it was bent upward. Like you're curving that function upward. And meanwhile, the function g is like you took a straight line and you curved it downward. So that curve thing is what we're going to call concavity. Like we're going to say at the end that f is concave up between 1 and 6, and g is concave down. So we're going to define that notion first. So next is the definition. It's actually an intuitive definition. Okay, so there's a lot of ways you can define concavity. I'm just going to use a way that relates to tangent lines. So if you have a function like f, like I have the same graph here, this is still f and g from before. If you have a function such that when you draw tangent lines for the function at different points, and those lines are below the functions, or another way to say this is to say that the graph is curved above these tangent line, you're going to say that this function is concave up. But if you have a function such that when you draw the tangent line, those lines are above the graph of the function, or if the function if the function is curved below those tangent line, you're going to say that the function is concave down. Of course, there's another simpler way. Like for me, I really like food. So for me, when I look at f, I can think of f as if it was part of a bowl facing up. So it's concave up. And when I look at g, I see g as part of a bowl facing down. So it's concave down. So this is how I do it. So it's like a super intuitive version, like the pig version, like, oh, he's thinking about bowls of food. All right. And here, just like increasing and decreasing in this class, every single interval, when you're going to talk about increasing or decreasing or concavity, concave up or concave down, we're going to be using open intervals. Always, always open. Okay, so, and if you have a point where the function goes from a bowl facing up to a bowl facing down or vice versa, so if you have a change of concavity, we're going to call these points inflection points. Okay, so they're very, very special point. So the first thing we're going to do together is look at examples, and we're going to label on a graph where a function is concave up, concave down, and where is a function have as any inflection points. So here we go. Let's find for the following functions where the function is concave up and concave down, and find any inflection point for the function. So here I'm going to use some notation. For concave up, I'm going to write f is smiling upward, like a grandma, okay? Or if f is concave down, I'm going to say like f is smiling downward, okay, like a grandpa. And if there's any inflection point, I'm just going to label them in the IP part. All right, so here we go. So we start at the beginning, okay, and then just by tracing the function, I'm going to find bowls that are facing down or up. So here I see that my first bowl, and be careful, increasing and decreasing has nothing to do with concavity, okay? So you have to kind of think about those two things, those two descriptors at two different times. Okay, so here my function is first a bowl that is facing down. So my function is concave down between A and B. So the first interval here of concavity is A and B, and this function is concave down. So here between A and B, the function is concave down, open intervals here. Then afterwards, the function is concave up between B and C. So I have my function that is concave up between B and C. Because we go from concave down to concave up, this means that B is the first inflection point for that function. And then the function goes from concave up to concave down. So it's concave down between C and D. So I have an interval where it's concave down, so CD. So I'm just going to glue this. So between C and D, oh, my U is ugly, you won't see that, but it's concave down. And then afterwards, so this means that C is an inflection point because we went from concave up to concave down. So C is an inflection point. Then what about D? So D is part of a bowl that is facing up, one bowl here that is facing up. So concave up between D and E. So between D and E, the function is concave up. So this means that D is another inflection point. You went from a bowl that is facing down to facing up. So D is an inflection point. What about E and P? So here, when you're just using intuition, you might think that, okay, this is concave up to concave up, so maybe I should just say concave up everywhere. I think the bowl intuition is the way to go here. Yes, between E and P, it's again concave up, but it's not part of the same bowl. Okay, so if it's not part of the same bowl, it's not part of the same interval of concavity. So E is not an inflection point because you stay concave up around E, but we write these two intervals separately because they're not part of the same bowl. And then afterwards, between P and Q, I have a function that is now facing down, concave down. So this means that P is the last inflection point for that function. And so for endpoints, we don't say anything. But then again here, when we're going to describe function in general, like A and Q will have their own moment of glory, where A is a local minimum. It's actually a global minimum. Q is a local minimum. And then, of course, we'll talk about increasing and decreasing too for that function. So there's other things going on. And same thing for E. Yes, E is not an inflection point, but it's a local maximum. And potentially, it's hard to tell here, but I think it's also the global maximum. So, we're not forgetting anyone. Okay, so everything is going to be use somewhere, to describe that function. Let's look at one other example. So down here, I have a function that is initially concave up all the way up to 2. So my function is concave up from minus infinity to minus 2. And then between minus 2 to 2, I have a bowl that is facing down. So between minus 2 and 2, and then finally my function is concave up between 2 to infinity, so 2 to infinity. So this means that minus 2 and 2 are inflection points because I went from concave up to concave down to concave up. Okay, so I have a change of concavity at minus 2 and at 2. So those 2 points are inflection point. Again, when you have the graph in your face, it's easy, okay, or easier to see the concavity and inflection points. But the true challenge, and this is where we're going this is what we're going to study next, is how can you compute concavity? Okay, so that's the true challenge. So it's just like increasing and decreasing, local min, local max. Concavity will be a computation at some point. We've answered for increasing, decreasing, local min, local max with the sine table of f prime, and we will answer with something similar, the sine table of f prime prime, okay, for concavity. All right, but for that first video about concavity, that's it, that's all. Bye-bye, miss you.